I thought I was unmuted. Oh, no. Okay. Cool. All right, so I want to start off by talking about the engineering problem we're trying to solve. So very common in engineering and in science, there are these things called agent-based models, and they have agents and they interact in various ways, and there's not much more you can say in general about them. And that's a problem because we want to have some sort of more structure to these models because we want to have people communicate their models to each other and have some form of representation that isn't just the code, the implementation of the model. We want some higher level structure that we can think about these models to help us do high level things like comparing models or combining them or editing them. And so this would be the state of the art where corresponding to these three examples of agent-based models where you have a game of life and sheeps and wolves eating each other and COVID modeling, the state of the art is that the way that we represent these models is just pieces of code. And I think part of our philosophy of applied category theory is that general purpose code is not a great syntax for scientific modeling. There's a lot of virtues that we get when we work with our model being in a nice syntax category, such as presheaves or poly, that we can then give a computational semantics to. And then we can do things like limits and colimits and substitution in our nice syntax category. So I think that a great example of this applied category theory philosophy is the idea of span rewriting. So there's this idea that we can take spans in some category, in an adhesive category, and basically interpret them as rewrite rules, where on the left-hand side, I have a pattern that I'm looking for. On the right-hand side, I have something I want to replace it with. And then I can take some input graph, let's say here. I don't know if my mouse is, it's not showing, yeah. Okay, maybe I'll just look here, okay. So our input graph is going to have a match morphism from the pattern that's just going to tell us where to apply that rewrite rule, and then we can actually just compute it via the semantics of taking a push-out complement and then a push-out. There's lots of other ways that we can do this, but the idea is that this is a nice syntax for something that ordinarily people would use a piece of software, a piece of code to do some sort of data manipulation. So this is great for small local changes, but now we want to say, well, how do I combine these rewrite rules into a greater program? How do I have an entire flow of these rewrite rules where especially I want to be able to control what the matches are? And so as an example problem, I might say this will be a sort of running problem. This is a very contrived example, but let's say we have a graph and we want to say for every vertex, if it has no neighbors, delete it. And otherwise, we're going to look at all of its outgoing neighbors, and then we'll flip a coin and we'll add a loop to that other vertex if it's heads. And so really, if we want to accomplish these goals here, one way that we can do that is to just make an arbitrary program in our programming language, and the only way we're allowed to modify our input graph is to call applying rewrite rules, where we assume we have access to some library of rewrites. And this is okay. I think this is actually an improvement over the state of the art where it's just complete code all the way through with even no distinction of rewrite rules. But still, overall, our model is a piece of code. This means that I can't do high-level things with it the way I want to. Rather, what I'm going to talk about is a category where the morphisms are these agent-based models, and we're going to understand that category pretty well. And rather than try to build up to the punchline, I do want to just show the punchline that we're going to build up to. So I hope that by the end we'll be able to understand this diagram here, where this wiring diagram actually does correspond to what this program on the right is computing. But we actually understand this as a composite of some primitive morphisms. On the bottom, they're sort of like, as we go into any box, this is sort of like the before and the after. And I'm going to try to explain how we interpret what category we're interpreting this wiring diagram in, and what actually is going inside these boxes. So that's just a sneak preview for what we're building up to. Maybe some people yesterday got to see some algebraic Julia stuff, so we can, this is actually a live notebook, also a presentation, so this is all the output of code that you could run yourself. We can import CatLab and use some of its native support for the category of co-presheaves on the schema. And we can visualize that. And what probably wasn't mentioned yesterday is that algebraic rewriting is a library that extends this with a lot of constructions from graph transformation. So we can actually we can create this rewrite rule by saying I want a rule that has the data of that span. I can apply that rewrite rule to a graph, and if I don't specify which match morphism I'm going to use, it will pick an arbitrary one. So here I took the path graph and I applied the rule, and it just gave a loop to the first one. So that's sort of the preliminaries, and now I want to sort of introduce this category in which morphisms are the agent-based models that we want to represent. And our starting point is Mealy machines, which we also call dynamic functions, because they're like a function from A to B that whenever you run it, it has its own internal state, and that internal state can change depending on your input. We can actually think of the morphism, we can actually think of the rewrite rules as as functions which are a trivial case of these Mealy machines where they have trivial state. And we can actually think of a rewrite rule as having two possible outputs, one in which you successfully apply the rewrite rule, and one in which you don't successfully apply the rewrite rule. So here is the code for taking our rule that we defined before. We can wrap it in this rule app thing and get a rule app box. And now we can actually apply that to, if we apply it to an empty graph, well then if we look at the second output, which is this bottom one, then we can see that we get an empty graph out of it. And if we actually pass it in a non-empty graph, then it will be able to apply this add loop rule. And then we can see the first output is going to have the same thing we had before. So now I want to talk about how are we going to actually control what our matches are. So I think this is very related to the idea of specifically agent-based modeling. And the idea is that we want to have an agent be this object of a co-slice category, that we have some state of the world, let's call it X, and you have a shape of an agent, A, and a map into X is basically going to pick out that agent. So this is a very flexible notion of agent. It's basically any possible sub-object that you could identify. And so before, when we had this add loop box, it was basically saying add a loop to some vertex, I don't know which one. But now if we have the ability of saying, actually, I'm going to have my input be maps from a vertex into some other graph, what I'm saying is I'm giving you a graph with a distinguished vertex. I could think of the vertex as the active agent, and this add loop rule being saying, this is what the agent is doing. It's adding a loop to itself, let's say. So if I feed it in this graph, I'm going to get out a loop added to that particular distinguished vertex. And so this is actually going to require a little bit more data than the span of just a vanilla rewrite rule, because we need to distinguish how does that interface actually relate to the rewrite rule. So our input agent, the thing coming on the wire into it, is going to have to be related to our pattern that we're going to do the rewrite rule with. And we also need to have an output agent, which we can then compose with this resulting morphism to basically get what the output is. And so as an example of this, we can actually, here's an example of composing two rewrite rules in a row. One is adding a loop, and the other is deleting a vertex. If I feed into this whole process again, our path graph, but now we're going to have the second vertex being distinguished. If we run it through this whole pipeline, it's going to go through add loop and add a loop to the second vertex, and then it's going to go into delete vertex and actually exit the failure case, because we actually can't delete any of these vertices. All the vertices are connected to other things. So there's this notion of like, you can't delete a vertex that's connected to other things by itself, because you'll leave sort of dangling edges. And that wouldn't be a valid application of a rewrite rule. But either way, so you can see that our second result is going to have the graph we were expecting. So all of the Mealy machines I've shown you so far were just these rewrite rules that have no internal state, but what makes Mealy machines exciting is that they do have internal state. So we're going to now talk about a for loop, which is going to be a Mealy machine that has an internal state of natural numbers. And when the internal state is 0, you're going to exit out the bottom wire. Otherwise, you'll exit out the top wire. And so now we can actually compose some of these morphisms together. So we might say this is going to be adding, this whole composite morphism is add 2 loops. And we can see what happens when we apply that. And in general, we want to maintain some good separation of concerns. So we're going to say that these reddish boxes are going to be control flow boxes, which cannot change the state at all. And the rewrite rules don't have any internal state, but they're the things that can actually modify what the state of the world is. And that's sort of going to keep things very clean so that we know what blue boxes are doing and what red boxes are doing. Red boxes like this for loop here, they change their internal state, but they don't change the state of the world, the thing that's flowing into it and flowing out of it. It's just effectively redirecting you out of redirecting your input into one of its outputs. So as an example, and then I'll take questions because I would like this little miniature composite to make sense to everyone in the room. This box here is a box that looks like an ordinary rewrite rule from the outside. You feed something in, there's two possible outputs. But the first 3 times you run this rewrite rule, it looks like the add loop rule. And any subsequent times you actually run this function, it's going to look like the delete vertex rule. And you can see that's from how it's wired together. So I'm hoping that this notion of combining control flow and rewrite rules is making sense. So if there's no questions, then I want to talk about something because I see someone raise their hand. You're free to unmute and say.
Yeah, just a simple question. How are you merging the wires? What does that mean?
How are we what, sorry?
You are merging the wires just before you output them.
Yes, so I'm taking advantage of the symmetric monoidal structure of set with the monoidal product being the coproduct. So I'm able to, I do have some extra resources, not just a vanilla SMC, but I actually can inherit a lot of structure from set. But actually,
when you evaluate yes, the mergers, only one output will be active.
Yes.
Okay.
Cool. Question?
Is the boundary of this part of the diagram using for illustration, is this loop on the outside part of
is the loop?
It seems like there's feedback.
I don't see any
outer
feedback.
Box. Is that true, or is that just a box for illustration?
Yeah, the outer box is just for illustration in the sense that you can imagine substituting this into some hole that has one input and two outputs.
Okay.
Yes.
Thank you.
Great. So it's good that we're talking about the relationship with set because actually this monoidal product is the coproduct in set, but it's not actually the coproduct in this category of Mealy machines. And that's because that actually some required things that should be equal aren't actually equal. For example, it turns out that the state spaces of this morphism on the left and this morphism on the right are not literally equal because they have different state spaces, but they have the same behavior. Essentially, this G morphism there with its extra state space T is not playing any particular role. It's effectively not being used. So what we actually want to take away from this is that the real thing that we care about is how these morphisms behave. And we want to think of these Mealy machines as just presentations of our real mathematical object of study. And so the real thing we care about, we can actually represent as behavior trees. So the idea of a morphism A to B as a behavior tree is to say that the nodes of this tree are functions from A to B, and then for every value of A, you're going to branch and get a new behavior tree. And this is basically encoding the fact that your state is somehow changing when for every possible input value you have. So again, this add loop example is going to be, and I can't draw an infinite number of edges for every single possible directed graph, but you can imagine that all of these edges are pointing to the same thing, and that I run this function 3 times, and then suddenly it just looks like a delete vertex. And actually, to simplify this issue of drawing infinite graphs, in a special situation where how the state changes is just dependent on what input wire you come in on, we can actually just draw it branching based on the input wires. Let me just show a simple example of this. So we could draw this example, which has 2 input wires, as a binary branching tree, where if I come in on the left wire, the the effective function that this thing is computing does not change. But as soon as I take the right wire just once, it's going to look like, it's going to behave like this, where if you come on the top wire, it's going to look like add loop, and if you go in on the bottom wire, it's looking like delete vertex. And I want to show that actually this digression into the sort of mathematical underpinning of these morphisms is actually really informing our computational implementation. So we can take our rule app box and interpret it as a Mealy machine, and then interpret that as a behavior tree. And because these behavior trees are infinite, we need to lazily explore them. So it'll start off being empty, and then as we actually evaluate that behavior tree on some input, we can then look in its internal, it computes a bunch of stuff, and then we can look that its internal state has now cached some of the behavior tree that it's explored so far. So let me talk about what actually this set of behavior trees is. It turns out that we can actually think of all the possible behavior trees as, for an interface A to B, as essentially starting with some polynomial functor, the internal HOM from AY to BY, and then if we apply this co-free comonad functor to that, we actually get a category where the objects are these behavior trees. And cat sharp here is this category of categories and cofunctors. And while we could just look at the behavior trees as the objects, if we actually don't throw away the whole category structure there, and we actually say, no, between every object in my category A and B, I actually have a whole category of morphisms. So I have essentially morphisms between my agent-based models. That's actually really important structure that we don't want to throw away, because those morphisms are actually important here. They're actually encoding how the system updates. It turns out that a morphism between two behavior trees is basically taking a path in that tree. Yes, Kevin?
Has there been a Kleisli category yet? I'm just trying to stay where I am.
That's the next slide, yeah. So the last bell and whistle that I need to show, just to fully explain what's going on, is that we can generalize this idea where our polynomial functor is AY to BY, and rather we can actually compose with a polynomial monad T. And this is going to allow us, this is going to give us a lot of more generality for free, in the sense that we can very easily say, give this rewrite rule box a non-deterministic semantics, which says that rather than picking an arbitrary match morphism, we're going to say, give me a list of outputs for applying to any possible match you find. And likewise, we can use this lottery monad to basically say that we actually, rather than doing some sort of pseudo-random thing that you have to sample, we can actually compute these probabilities of all the possible outputs. So I want to just show on this slide how the actual computation works, where if we're composing F, G, and H, these primitive morphisms, we can actually maintain 3 independent behavior trees that start out all empty or just with their roots. And if we were to feed in a B1 input to this, then this F tree will then grow 1. And then maybe that goes into G, which spits out 3 possible outputs, and those outputs feed back into F, which then causes that to branch, and those outputs can go into G. So we're essentially running these trajectories through our system and simultaneously building up all of our behavior trees, computing as much as necessary, and ultimately all of our trajectories will collect at our outports, and that will be our result of our computation. So importantly, we really want this trace structure, and we have a trace morphism basically allowing us to make sense of what's going on when we feed loop. We have these feedback loops. The category of sets and partial functions is traced, and it has this, if you look at that trace structure, it sort of has the semantics of running your partial function, sort of a computational semantics. And when we actually, so the category that we're working with is enriched in cat sharp. There is the ordinary underlying category, which can take you back to an unenriched category. And when you do that for the maybe monad here, then you're going to actually get the category of sets and partial functions. And it turns out that our conjectured trace operation ends up corresponding to the trace operator for, that is already the trace operator for sets and partial functions. So what is like an advantage of enriching in cat-sharp? Well, I think one really cool thing which influenced our implementation is why were we licensed to have 3 independent behavior trees that we're building up as opposed to having to make one big behavior tree? And the reason for that is that when we compose, let's say, phi and psi together, we're composing these 2 small behavior trees to get a big one. When we compose the behavior trees, we actually, while we compose the behavior trees, what we get is a decomposition of the behaviors. And this is related to polymorphisms being forward on positions, which are the trees, and backwards on directions, which are the ways of updating. So I can take any path in my composite tree, and I can actually obtain, canonically, paths for the corresponding behavior trees that I composed to get together. So this is essentially, we're using this trick in order to inform our implementation of having individual behavior trees for all of our primitive morphisms. And that's how we're maintaining, updating the entire state, even for a large composite of morphisms. So we have almost everything we need in place to make sense of our solution, but we need some other, and so these rule applications and control flows are really doing the heavy lifting for these models, but we need a couple other primitive operations in order to manage switching control from agent to agent. So how do we say something like do X for all vertices? So the thing that's going to allow us to do that is we're going to make a yellow box for it, and we're going to call it a query box. And this is going to have the semantics of when you enter in on the left-hand side, imagine that as like hitting the reset button. And when we enter that, we're going to query for all agents of shape B, and we're going to basically run that routine for each one of them. And then when we're done with that, we're going to exit out this leftmost port. So in this specific case, if we were to say that I want to add loop to every vertex, then I'm going to feed the second output into the add loop box, and then feed that output back into the second input. And so this now has the semantics of doing this for every vertex. You can see we're labeling the edges with what the shape of the agent is that's living on that wire. And when we apply that schedule to the path graph, if we call this whole thing a schedule or a recipe, then you can see we've added exactly 1 loop to every graph, or to every vertex. So the last one that I want to show is this weaken thing. And it's helpful because we often want to, we have some sort of distinguished subobject, and we want to switch to a smaller subobject. So a morphism from A to B is going to convert B agents into A agents. In this case, if I have a distinguished edge, then it should be straightforward with the data of a morphism from a vertex into the edge to obtain a distinguished vertex. And the way this works is this, the data that's coming in is a map from, let's say, A into the state of the world. And if we pre-compose that with this morphism living in this box, then we're going to get a morphism from B into the world. And we also want to have a failure box just for hitting edge cases that we don't expect to hit. So this is putting this all together. We're going to essentially, well, let me just show what this looks like. So this graph right here, which we've constructed with this code here, is basically what do we want to do for every single edge. So I wrote here in my sort of natural language description of what's going on for all edges V to V prime. So for each of those edges, what I want to do is I want to switch my focus to the target. I want to flip a coin, and if the coin is heads, I want to add a loop. Now, in order to do that for every edge, I basically want to wrap this recipe in an agent. We have a constructor called agent, which makes it very easy to just say, well, I want to do this as a subroutine for every single edge. So you obtain this schedule, and then we want to essentially say, well, we want to do this thing for every single edge. We have a distinguished vertex, but we want to do that in the case that V does have neighbors. And so if we look at this delete vertex box, delete vertex will delete the vertex if it doesn't have neighbors, and otherwise it will exit this wire. So our overall program really is just feeding that case into this previous recipe that we have right here. And if we do that for every single vertex, we'll essentially have replaced the piece of code that we wanted with this composite of what, 1, 2, 3, 4, 5, 6, 7, basically seven boxes. But we no longer have the syntax of this, I guess, arbitrary Julia, but we can actually now do things like data migration, we can do substitution, we can compose this, and we can also do things like give this a non-deterministic or probabilistic semantics. So if I didn't make the frame rate too fast, then you might be able to follow how we're entering in the query box, we're looking at this vertex, I think we lose the coin flip, so now we're moving to the second vertex, and here we actually do succeed the coin toss, and we've added the loop, and we essentially do that for every vertex. So this is sort of the punchline, but I think the more interesting examples, that's something that might be able to be covered in a short demo. I think more interesting are examples like encoding the game of life in this formalism. This is our depiction of the wolf-sheep interaction demo, where we have a schedule for that. We've actually applied this to real COVID models that have been used in practice to try to understand this as a potential formalism for scientists to communicate with each other. That's not just spaghetti Python code. And we also have a blog post which sort of explains this in other ways. So I also would have loved to have time to talk about performance, because what we have currently available on Algebraic Julia is a reference implementation, which does things more rigorously, but has a lot of performance improvements to be made. But we've also been making lots of performance improvements that we're hoping to merge in the near future. And there's lots of interesting mathematical and engineering problems for how you would make this compile, how you would give one of these diagrams a computational semantics that is equally efficient to what someone would write themselves. So yeah, and we also have a paper for people who want to check that out. So thank you.
We might have time for one very quick question.
Hi. Could you go back to the slide, the very first slide where you introduce the box that does a for loop?
The box that does a for loop. Yes, here.
Oh, I think I meant the next one. There we go. So I would naively expect the for loop to be at the end. If the computation is going from left to right, you would like compute the things, and then the control box, the for loop, decides which one to actually output. So that's not what's happening here. So why is the for loop at the beginning? I must be missing something basic about
yeah,
the
so I'm coming in with a graph I'm thinking of this as a function that I can run. I can feed it in a graph with one vertex. That one vertex enters here. We check the internal state. It's equal to 3. So we take the upper path and we actually add a loop. Then I feed it another graph, and now the internal state is 2. And I exit the top thing. And now I feed it another graph, and it will say, okay, my state is 1. So now I'll still add a loop to it. But now if I give it another graph, it's going to say, well, my state is 0. I'm going to delete a vertex. So it is still flowing from left to right. So yeah, maybe something there's counterintuitive.
That makes sense. And then why do both of the blue boxes output on both the top and the bottom?
Yeah, so this is how we are defining these rewrite rule boxes, which is the top output is going to be a successful application of the rewrite rule, and the bottom output will be I failed to apply the rule. And so it's nice to collect, rather than having 4 outputs, it's nice to collect the like outputs.
Okay, thank you.
Sure.
Okay, let's finish there and thank our speaker again.